Vê aí se chega a notificação. Acho que é 120. Mas acho que os que eu perdi é 120, só como eu perdi os 4 lá, por causa da minha currículo. Ah, não, mas esse caiu aí, não. Não deve ter caído aí. Eu já passei, só falta passar em prova.
Foi automática mesmo?
Sim, foi automático.
Tá online, cara. Ian.
Tá piscando essa luz, né? Ah, podia não estar piscando essa luz.
Tá bastante.
Cara, você acha que o Ian não funciona? O Ian é muito competente.
O que você me perguntou? Você me perguntou quando que eu falava pra você?
Aquela coisa foi um sucesso, sei lá. Então pode não perder o dela. Só que é brincadeira. Foi quase.
Mas foi
Foi presente. Ah, mas sei lá, não tinha muito mais que diferença. Eu teria que mudar lá o negócio de metadados, transmissão.
pra esse canal.
Mas depois eu uso, né?
Precisa fazer isso pra todo stream, você vai fazer na descrição.
Quer dizer, não sei, o cara não sabe.
Mas o que o Carlinhos tem a ver com isso?
Pagar?
Não. Você vai ficar aqui, Russo?
Sim, mas é ele que faz a ponte, né?
Não. A tua está perguntando aí pra gente vai.
Ah, ele vai pagar.
Ô, galerinha do IP. Tá escrito.
Começando a conversa com ele lá. Só quanto número de pessoas? Vamos fazer uma vinheta. Hora do tempo, vamos já.
Vai ter, no pausa vai ter uma apresentação de Sussu.
Você é o primeiro.
Vai ser o programa do intervalo, né? A gente entrevista você, vocês que estão acompanhando hoje a aula aí, muito boa, né? Muito boa. Segundo dia, muita surpresa.
All right. Good morning, everybody. Yeah, so I hope you liked the problems yesterday. Today, the first part of this morning session, I will go over those problems. I will try to fill in some blanks with the solutions. I think you probably have discussed many of them, so I'll start briefly, but should you have any more questions about anything in the problems, feel free to ask.
É que tem uma aqui.
Okay, so let's start with some of the easy ones. One of the easy problems was this problem about merge sort with square root. So we are sorting an array of size n. What we do is we split it into square root of n and n minus square root of n, and we recurse. And the task was to sum all of the vertices that will appear in the recursion tree. So if we start with the maximum value of n, 10 to the 9, 10 to the 9, the square root of this is something like 30,000. So the first split of the recursion tree will be something like 30,000 and 10 to the 9 minus 30,000, which is approximately 10 to the 9. And this will continue like this, so this will be something slightly smaller than this one, and still something that is close to a billion, and so on. And now, the thing to realize here is that the size of the tree is quite large if you actually just implement the code from the problem statement and run it for 10 to the 9. You will see that it runs too long. So it will not finish in time, and we need to do something smarter. And the something smarter thing to notice is that this step is reasonably large. As long as n is greater or equal than 10 to the 6, the square root of n is greater than or equal to 1000. So each time we have an n that is more than a million, we will remove at least 1000 from this value. So we start with a billion with 10 to the 9, and we do 1000 steps. In each of them, we will remove at least 1000 from the number. We will certainly get below a million. So this means that there is only a very few calls with the large values of n, and most of the work is done also probably with a small size. And as those are repeated, the easiest solution is that we can apply memorization. So the whole solution can be implemented in 5 lines of code. You just implement the exact thing that was given in the problem statement, and you add memorization. Whenever I already handled this particular n, just look into memory and output the answer. So the easiest way to do this was with the map. If n is in the map, return map of n, and if n is not in the map, then do the recursive calls, sum up those values, and store it into the map before returning it. Another way of solving this problem would be by doing straightforward dynamic programming. So we can pre-compute the answers from 1, let's say, to 10 to the 6 to 1 million by just going from the left to the right. For 1, the answer is I think 0, and so on. And if you want to know this answer, then it is n for some k, and this k, plus this answer, which is square root of k, plus this answer, which is k minus square root of k. So we just go from the left to the right with this array. You pre-compute the answers up to 10 to the 6, and then you run this recursive algorithm with the change that whenever you get below a million, you can already answer. This will also be fast enough, but the previous solution is easier to code. Okay, questions? If not, moving on. Another easy problem was the problem even roads. So in this problem, we are given a graph. We have a starting vertex A, we have a destination vertex B, and we are looking for the shortest path that has an even number of roads, so the length would be 1, 1, and 1. This is only 3. If these were 3 and the 4, this is 7, which is longer, but this one has an even number of roads, and this one has an odd number of roads, so it's not usable. How can we solve this task? By simply remembering in the state, not just the vertex where we are, but the parity of the number of edges we have already used. In other words, you can imagine having 2 copies of this graph, and each edge is going not within the same copy, but from one copy to another. So it's to start in the copy on the back, and in the first step you go to the copy on the front. In the second step you go to the back again, and so on. And you want to go from the vertex A in the back copy to the vertex B in the back copy. And this will guarantee that you will the length of the path will be minimal and the number of edges used will be even. So we built a new graph with 2n vertices, and then we just run the standard Dijkstra's algorithm on this new graph. So each vertex is a vertex of the original graph and the parity bit. And as the graph was large, we needed the efficient implementation of Dijkstra's algorithm, which runs in any time in the priority queue. And that's it for this task. Okay, any questions about this one? If not, moving on. The next problem, for example, the problem about the 7 dwarfs. In this problem, we are buying candies for the 7 dwarfs. We have some options, A1 through AN. And we are looking for a subset of these, which has the maximum possible sum with the given constraint that the sum has to be divisible by 7, because each of the dwarfs has to get the same amount of candy. So there are two different approaches to solving this task. One of the more standard one is dynamic programming. We need to make sure that we don't forget any case, and the easiest way of not forgetting to handle any case is handling all of them, trying out all possibilities. So what we will be doing is we will be adding the bags of candy one at a time, and each time we will recompute new answers, and the new answers will be as follows. So if we have two options of buying candy that give the same remainder modulo 7, then only the larger one is interesting for us. So if we can buy 103 candies, or we can buy 703 candies, then definitely we want to buy 703 candies, and we don't care about the other option, because any set of additional packages that will make the first one a viable solution will also work for the second one, and vice versa. So what we need to do is for each remainder, that is for the values 0 through 6, remember the best solution so far. So at the beginning, before we vote anything, the best solutions are for 0, the best solution is 0, and for other remainders, 1 through 6, the best solution is minus infinity, because we don't have any option of buying such a set of candies. And now, whenever we get a new package of candy, either we don't use it, and if we don't use it, the previously computed values are the optimal ones, or we do use it, and then we can take any of these values and add the package of candy and improve one of the remainders. So for example, if A1 equals 3, the only thing that will change is that if we decide to take it, then we can take this optimal set with remainder 0, which is 0, add this package, and get a 3 here. And then, if A2 is 71, we can apply it both from here and from there. And we will have a new way of getting to remainder 1, which is 0 plus 71. And we will also have 74 here. And now if, for example, A3 would be 10, which gives remainder 3 modulo 7, one of the things that would change is that we can go from 71, so from remainder 1 to remainder 4 by adding these 10, and this is better than what we had. So this 74 will change to 71 plus 10, which is 81. So each time you take the original 7 values you have in this array, and you try adding the new value to each of them and improving one of those values. And in this way, after processing each bag of candy, for each remainder, you have the best solution so far. And the answer is the answer for remainder 0 at the very end. So that you have, in some sense, tried all the possibilities, and the only optimization you need is that after each step, you discard those that were improved by other possibilities. So this runs in linear time and is clearly optimal. Okay, any questions about this one? So now I will show you a different solution, one that people come up with less frequently. And the most interesting part of the solution is a general lemma from number theory. And the lemma looks as follows. Suppose you have numbers x1 through xn, which are some integers. Then there is always a non-empty subset of these numbers, which is divisible by n. And this is a very weak statement because we can actually show that there is such a subset with a very specific form. Here's what we can do. We can look at the following sums. x1 plus x2, x1 plus x2 plus x3, and all the way through x1 plus xn, the sum of all of the numbers. And now there are two possibilities. One possibility is that one of these sums is divisible by n. If this is the case, we have already won. And if not, we have n different sums, and as the remainder 0 is never present, we have only n minus 1 different remainders. So by the pigeonhole principle, two of these sums have to give the same remainder modulo n. So x1 plus x1 plus xi equals x1 plus and so on plus xj modulo n. And if this is the case, then we have the non-empty subset xi plus 1 plus all the way through xj is divisible by n. So regardless of what these numbers look like, there is always a subset of those numbers that is divisible by n. And this is something we can apply in our problem, the problem with the dwarfs. So the realization here is that whenever you have 7 packages of candies, there will be some subset of those packages that is divisible by 7. And what this tells you is that the optimal solution certainly has the property that we will leave in the store at most 6 of the packages. Because if you had any solution that leaves 7 or more packages in the store, then suddenly out of those 7 packages in the store, you could find a subset you could still buy without making the solution worse. So if you have this insight from number theory, you suddenly know something useful about this problem. That the solution has to be somehow small. So we could find the solution by in a time proportional to n choose 6, roughly. Trying all possible possibilities for 6 items. But this is still too slow for the given n. We need to do one more step of thinking, but we are almost there. And the one more step of thinking is that we don't need to try all of the possible bags of candies. Obviously, we just need to try the small sets of candies to be the ones left in the store. So what can we do is we can take all of the bags of candies and divide them according to the remainder. And within each remainder, we can sort them from the smallest bag to the largest bag. And now what we can tell is that the following. So first of all, we definitely want to take all of these. If you have a bag of candies, which is a multiple of 7, then you want it. There is no point with leaving it in the store. And for each of these remainders, we know that in total, we will only leave at most 6 bags at the store. So for each remainder individually, only the first 6 items matter. Anything larger, you will definitely buy, because even if you decide to leave 6 of these in the store, it will be the 6 smallest ones. So all you need to take is for each remainder, the first 6 of the bags, or fewer if there are not that many. So this will leave you with at most 36 bags. And out of those, it is optimal to leave some small subset in the store. And now we got to the time complexity of 36 over 6, well, plus all the way to 36 over 0. So we just tried all these possibilities, which is already possible by brute force. So there is, in addition to the dynamic programming solution, there is a completely number-theoretic solution to this problem. You come up with some interesting observations, and then you finish it by brute force. So I thought this was pretty. This is a task with very different approaches. Okay, does it make sense? Are there any questions?
First, we get by read the solution largest for each remainder, and after we do brute force on just the largest for each remainder. It's a much simpler solution than dynamic programming.
Yeah, it might be. It's concept. Well, the actual final solution is conceptually easier. So what you do is you start reading. You take all of the bags with remainder 0, and for each of the other remainders, you buy all of the bags except for the 6 smallest ones, and then at the end you try some possibilities with brute force. So it doesn't require you to know the concepts of dynamic programming in order to solve the task. But still, if you do know dynamic programming, then the other solution is easier to implement. The code is shorter. It's just like 2 for cycles inside each other, and that's it. So for most contestants, I think the DP way is the way to solve this task. But it is interesting to encounter also this other idea, because it may be useful. Like, in particular, this lemma is something that does come up from time to time. Another context where you can encounter things like this are, for example, tasks when you are trying to pay a sum using the fewest amount of coins, when you are thinking about things like, here is a set of denominations, so set of values of coins and banknotes, and you are trying to decide whether or not a greedy algorithm will always be optimal, will always pay the sum with the smallest amount of money. So then some of the things you do with this problem involve this lemma about divisibility. Okay, next I will talk about a problem which many of you avoided, which is the problem of 3 candles. So in this problem, we are given a rather simple situation. There is one who has 3 candles. The candles have some times C1, C2, and C3, which is how long the candle number 1, candle number 2, and the candle number 3 is burning. And then we know that, so this is C1, maybe this is C2, or maybe this is C3. And there is an interval, possibly a non-empty interval, and all 3 candles were burning at the same time. We are given its length, T3. And there are some intervals where only 1 candle was burning, and we are given their total length, T1. And we are asked to find all possible values of T2, which is the time during which exactly 2 of the candles were burning. Now this problem has an easy part and a hard part, and this problem also has an easy approach and a hard approach. The easy part is to realize that there is only one candidate for the solution. Why? Well, because let's take a look at the total time a candle is producing light. One way of computing this total time is C1 plus C2 plus C3. So this counts this plus this plus this. Another way of counting the same amount of time, so the total length of these segments, is that T1 counts these, T3 counts this exactly once, but we have it 3 times, and T2 would count this and this, but we have it twice. So this has to be equal to T1 plus twice T2 plus 3 times T3. And we know all of these, so we can compute this, just a simple linear equation. This was the easy part. Now the hard part is that this candidate doesn't have to always be a valid solution, because there doesn't have to be such a configuration of candles that produces this. There are some obvious cases where this is not true. For example, if you get T2 negative, then this is obviously impossible. But even in cases when you get T2 positive, it may be the case that there is no such valid configuration. And there is a surprising amount of different possible configurations of those 3 candles that make it impossible. So there are, I think, like 4 different constraints you need to discover, 2 of them for the case when T3 is 0, and 2 of them for the case when T3 is non-zero. And if you forget any of them, we have test cases that will catch you. So it is possible to solve this task by just case analysis, by taking this possibility and trying to find out all of the inequalities that have to be satisfied. But this is the hard way to solve the task. This is the hard part of the solution. But there is also a very easy solution. And the very easy solution looks as follows. Now obviously, from the input, all of the values are integers, and here T2 is multiplied by 2. So if we do the computation, the candidate value of T2 will either be an integer, or it will be the half of the integer. And whenever we have a valid configuration of candles, it is easy to argue that we can shift some of those candles. Well, in theory, we are allowed to start burning the candles at any real numbers. But this doesn't make sense to do so. If we know that all of the intervals are integers or halves of integers, we can always shift the beginnings to start at integer points in time or half integer points in time. Or if we want to have an easier implementation, we can multiply everything by 2 and then only start at integer points in time. And additionally, we only have 3 different candles, and shifting all 3 of them in time by the same amount doesn't make much sense. So we can pick the first candle started burning at time 0, and then for the second candle, it only matters to try starting times that are reasonably close to this one, and for the third candle the same. The burning times are very small, I think those are integers between 0 and 180. So the easy solution to the 3 candles problem, and also if you are interested in debugging your still incorrect solution that try to do with these inequalities, is simply to use brute force. So fix the starting time for one candle at 0. For the second candle and the third candle, try all possible starting times within some reasonable interval. And each time you get a configuration of 3 candles, you can compute the values T1 and T3 to check whether they match the values given in the input. And if they do, then you have a valid solution and you output T2. And if you never find such a configuration, then you output that there is no solution. So a very simple solution with just a few lines of code, but you need to be able to think in this way. The hardest part of this problem to me is that most people nowadays in programming competitions are not trained to think about problems like this one. Are not trained to think about, hey, I can afford to try a million possibilities and see whether any of them works. You are trained to look for efficient algorithms to look at time complexity. So this is kind of like a curveball. Okay, any questions? problem is a problem about dragons. So in this problem, we have a countryside, or a kingdom of islands, because of the story, and there are some dragons. The dragons do nothing other than they grow. Each dragon starts with some number of heads. So let me see, I'll use the letters to use the drop statement. Okay. So each dragon has some SI, which is the starting number of heads, and GI is the number of heads it grows after each minute. So we have a dragon with SI heads, we get to chop some of them off, then GI new heads will grow, and so on the cycle. And we have some dragon slayers, and each dragon slayer is able to either cut off a head during a minute, or travel by an edge of the graph. Okay, so the first observation about this problem is obviously if you have a bunch of connected components, then you have to solve each of the connected components separately because the dragon slayers are not able to travel between those. So we simply solve each of the connected components separately and add together the results. Now what happens in an individual connected component? We can have more than one dragon inside the component, D1, D2, D3, D4, and so on. And for each dragon, we have two options. The first option is that we need to have enough dragon slayers to kill the dragon eventually. So if we have a dragon that is 3 plus 70 heads, which means if we leave the dragon alone, each minute it will grow 70 heads. As long as the connected component of this dragon contains 8 or more dragon slayers, then we will be eventually able to kill this dragon. We can leave it alone for any amount of time we want, but eventually all of the dragon slayers can gather in the dragon's location, and each minute the dragon will grow 7 new heads, but then we will chop off 8 of them, or more than 8. So as long as we have more than 7 dragon slayers, this dragon is guaranteed to die eventually. So one possibility of killing this dragon is having more than 7 dragon slayers within the entire connected component. But there is one other possibility of killing this dragon. And the other possibility is killing this dragon before it can grow any heads. So if this were the only dragon within its entire connected component, the optimal solution would not be to have 8 dragon slayers. The optimal solution would be to have 3 of them. All 3 will be starting at the same location as the dragon, and they will, during the very first minute, they will chop off those 3 heads before it has any chance to grow any new ones. So for each dragon, there are 2 options. Either we kill the dragon during the very first minute, for which we need this many dragon slayers in the dragon's location, and just focusing on this individual dragon. Or the other possibility is that we need to have enough dragon slayers within the entire connected component to kill the dragon eventually. So now, given this information, how exactly do we solve a connected component? So what we can do is we can take all of the dragons within the collective component, and we can sort them by the value GI. So we will have something like 13 plus 3k, 2 plus 4k, 7 plus 7k, 47 plus 7k, 2 plus 13k, and so on. Now, the smaller this number, the easier the dragon is to kill eventually. So there will be some boundary somewhere, maybe here, maybe at the very bottom, maybe somewhere in the middle, such that the actual number of dragon slayers you use is large enough to kill all of these dragons eventually. So if I kill all of these dragons eventually, I need to kill all of these dragons during the first minute. And in order to kill all of these dragons during the first minute, I need to have at least 2 dragon slayers for this one. And in order to kill all of these eventually, I need to have at least this many plus 1 dragon slayers in the entire component. So in general, what we do if we have a list like this, if we try that this is the boundary between the dragons killed eventually and dragons killed during the first minute, then we need the maximum of this many dragon slayers, so this plus this plus this plus this, or this many dragon slayers plus 1. And this can easily be checked in linear time, so you start here at the bottom and you just do this value plus 1, and then you are moving upwards, you are keeping this incremental sum, and you are always taking maximum of this and this plus 1, and the minimum over all choices of this one is the minimum number of dragon slayers we need.
If the dragons have the same growing rate, doesn't
It doesn't
matter
matter.
the values of this target?
No, because, well, you can actually try this, but it will never be optimal. The optimal value boundary will be either below them or above them.
Okay.
And because if you think about the boundary here, by shifting it downwards, you are just removing 47 from this sum, and you are not changing this value.
Yeah, that's
So you'll never be within a block of dragons with the same value. Or more precisely, if this is the optimal solution, then this is also the optimal solution. Okay, so these were the dragons. Now we are getting to the more interesting stuff. Alright. Okay, next problem we'll talk about is the problem about the product of digits. So, in this problem, we have a set of numbers that is 0, 1, 2, 10 to 100 minus 1. So this is exactly 10 to 100 different numbers. And we are for a given p, which is between 0 and 10 to the 18, so that it fits into a 64-bit integer. We want to count the size of the set x such that x belongs to s, and the product of digits of x equals p. So, how do we do this? Probably the most important thing to know about this problem is something about divisors of numbers. Because imagine that you want to have a number with the product of digits equal to p. So what this means is that you will have some number with at most 100 digits. Maybe these are some leading zeros which we ignore. And there are some digits that go on and on. And as you go from the left to the right and multiply these digits, after each step, you have to have a divisor of the number p. As soon as you get something that is not a divisor of p, you cannot fix it, because if you will be multiplying it by other values, it will not be a divisor of p anymore. So all of the intermediate products, as you are going from the left of the number to the right, have to be divisors of p. And the number of divisors of p is not that large. This is the main important information we need from this problem. There is a very easy theoretical result that tells you that the number of divisors of a number p is less than or equal to 2 times square root of p. Why is this the case? Well, because you can pair up those divisors. If you have p equals to k times L, then at least one of these divisors has to be less than or equal to square root of p, because they cannot be both larger than square root of p. If you have k is more than square root of p, and L is also more than square root of p, then k times L is more than the square root of p times the square root of p, which is p. So without going to generality, we can take k to be the smaller one and L to be the larger one. We have k is less than or equal to square root of p. So all of the divisors of p come in pairs, something up to the square root, and the result will take p divided by this divisor. So in order to actually find all of the divisors, you just need to loop with k starting from 1 going to square root of p. And each time whenever you find a k that divides p, then p divided by k is also a divisor. And in this way you will construct a set of all divisors, and this will be an upper bound of its size. Actually, the real maximum number of divisors grows even smaller. I believe that the actual math that is the function of that gives you the maximum number of divisors of a given n is something polylogarithmic in n. But the more important lesson is some kind of a rule of thumb that for values that fit into normal machine-sized integers, the maximum number of divisors behaves somehow like the cube root of n. So actually, if you look at all of these numbers between 0 and 10 to the 18, the maximum actual number of divisors a number can have is below 1 million. It's only something like 80,000. This would be a number of the form p equals 2 to something times 3 to something times 5 to something times 7 to something, and maybe even times 11. One of the numbers of this form is the number within this range that has the most divisors. And even for this number, the number of divisors is pretty small. So now this brings us to a solution for this problem that uses dynamic programming or equivalent memorization. The implementation of memorization is easier because those divisors have very different values. So what you can do is, when you are counting the size of this set, you can try two possibilities. One thing you will try is the number of digits in x. So if we have a positive value of p, then we know that x has between 1 and 100 digits. So we can try all of these possibilities and sum them up. So for each length L between 1 and 100, and for each I, which will be the initial digit of the number, between 1 and 9, if p modulo I is 0, so if the number can actually contain this digit, then you increment the answer by the value so L minus 1 and p divided by I. So what this means is we go through all possible lengths of our number, we go through all possibilities for the first digit. We only take the first digits that can be used. So for example, if the product of all digits should be 7, then we cannot start the number with a 2. Because any number that starts with a 2 will have an even product of digits, it is not 7. So we can only take those first digits that can be applied. And now we are asking the questions. What is the number of ways in which I can choose the remaining L minus 1 digits in such a way that the product of these digits will be p divided by I? And this is something we can do recursively. Solve for r remaining digits, and q is the remaining product. It's very simple. We try all possibilities for the next digits. So for all possibilities of n from 1 to 9, if q is divisible by n, the result of this function will be incremented by solve r minus 1 and q divided by n. Of course, you need to add two other things to the implementation of this function. One thing would be handling the base case. So if r equals 0, there are no remaining digits. We return 1 if the product is supposed to be 1, which is the empty product. And we return 0 otherwise, because if we ran out of digits and we still have to have a product of 17, we cannot do it. Or 18 or something that can actually be done from digits. We are only successful if we get to the end of the number and the remainder of the product is exactly 1, so we already cancelled out all of the parts of p.
Sorry, can you repeat the base case?
Okay. So the base case that goes here is if r equals 0 and q equals 1, return 1. If r equals 0 and q is greater than 1, return 0. In other words, there's exactly one way to have an empty sequence of digits with product 1, and there is 0 ways to have an empty sequence of digits with any other product.
Thank you.
And then the other thing you do, obviously, with this function is memorization. So for each combination r and q, we'll compute it only once. There are only up to 80,000 different divisors of p. There are only 100 possibilities for the value r, and this makes it running time. One thing that needed special handling was the possibility p equals 0, which is roughly the same code, but not exactly. For p equals 0, what will be the recursive function? This will be the number of remaining digits, and just a single flag whether we already have a product equal to 0 or not. So we start with the product, we start with L, which is again from 1 to 100, this is the length of the number. We start with the first digit, which has to be non-zero for the number to have this specific length. So for example, with the 7, this time all of them can be used. And we will be calling a special new function solve0. And solve0 will be getting only a true or a false. Initially it's a false. And in order to get a product of digits equal to 0, we need to use 0 at least once. So what we remember here is whether we already used at least 1 0 or not. And at the end, if we already used the 0, we return 1. And if we never use the 0, we are in an incorrect branch, we don't need to count. So we do essentially the same thing. Solve some problems. In how many ways can I fill in these digits arbitrarily, and in how many ways can I fill in these digits so that I will use at least 1 0. Instead of doing recursion here, you could actually do some very simple combinatories, because this is something that can also be counted. This is 10 to this minus 9 to this. Because 10 to this is all possibilities to fill in the digits, and 9 to this length is all possibilities to fill in just the non-zero digits. So you can just write a formula for this instead of running the recursive function. The final bit you need to remember is that for the case p equals 0, there is also a special case, which is the number 0 itself. So you need to do a +1 at the very end. Okay, so conceptually I think this task is not so difficult, but in practice it turns out to be a bit nasty, especially because it's designed to be hard to debug. Usually, in programming contests, you have test cases that are small, and you can use these to debug your solution. And when I was writing this problem, I intentionally made it so that the set S is constant. It is always 10 to the 100. And this makes the solution harder to debug because you always are dealing with a lot of numbers. And actually, a reasonably smart way to do the debugging would be to artificially decrease this from 100 to maybe a 3. So you had a solution that was buggy and you didn't know how to debug it. And you could write a brute force solution for just S, not up to 10 to the 100, but just the one up to 10 to the 3, which is 1000, or maybe up to 1 million. So you write a brute force solution that actually counts all of the values in the set, and then you compare this to your program. So in order to debug this program easily, you have to artificially decrease the size of the set before doing the debugging. Yeah?
You said in 0 case you have to do 10 to the size of the number,
Yeah.
minus 9 to the size of the number. If we do 10 to the size of the number, we are already computing the possibility that all the digits are equal to 0.
Yeah, so to be more precise, at least what I did in my solution, is I still kept these two loops.
Yeah.
So I'm counting all the numbers which have a product of digits equal to 0. There is a special case which is 0 itself, I have it separately, and all of the remaining numbers have some length between 1 and 100. Have some first digit which is not 0, which is between 1 and 9. And then if you fix this, so you fix the L, and you fix the I, then you have exactly n minus 1 digits to fill in, and here is what applies, so here you have answer plus equals 10 to L minus 1 minus 9 to L minus 1. Alright, anyone else?
Just a case where the of binary error for I to 9 instead from 0 to 9 any error of the storage and break the solution easily.
Yeah, so this is part of why I was talking about debugging your solution, because precisely it's very easy to forget about one of these cases that can go wrong, especially if you are trying to hide, if you are trying to come up with solutions as quickly as possible.
E o de sorte também. Como vocês chegaram? Zero. Oba. A gente chegou menos 1, 0. Não precisa fazer maior de 1. É só simplificar.
4 problems left. Next problem for today, does it sort? In this problem, we were given the description of something that is related to a comparator network, but it has also one additional operation, which could take an entire block of lines and sort those. And the question was whether or not this program actually sorts. So in general, there is a lot of theory about these so-called comparator networks. So the basic building stone is just a simple thing that we will also have in this problem statement. This is called a comparator, and it works a bit like this. So at the beginning, you have a collection of inputs. So this is the input array from the first element to the last element. And then the basic operation you can do, you can compare two of the elements and swap them if they are in the correct order. So after you do this operation, you will have the minimum of x and y here, and the maximum of x and y there. You can imagine this as an actual physical collection of wires that are going from the left to the right, and whenever you apply a comparator, then those two values are swapped. And we can certainly build a sorting network just out of these comparators, because, well, obviously many of the actual sorting algorithms can be implemented in such a way. One very easy example would be bubble sort. In order to do one iteration of bubble sort, you can just compare the values like this. So this is what is done with actual bubble sort. You compare these two, and you get the minimum, and you put it here, and you get the minimum, and put it there. And now you get the minimum of this wire. And then you do the same with twice, and then you do the same thing again, and you have sorted those numbers. Of course, this runs in quarter of time, but it works. And now, so the other type of the operation that was given in the problem statement, that you just take a range of the array and sort, can also be seen as a small sorting network, so a small collection of these comparators. So anything we have in the input is a sorting network like this one. And the question is whether it does sort or not. Now again, this problem has two different ways of being solved. One of them is painful and leads to potentially many wrong answers as we are keeping it constant. Because one of the ways is to guess that I have the time to try a lot of different permutations of the input array. And if it doesn't sort, it probably should come up sometimes during those tests. So you can actually squeeze through a well-tuned solution that tries just enough possibilities to fit within the allowed time limit and to discover whether all of them pass, in which case we claim that the network works, or whether we find a counterexample in which case we claim that it doesn't work. But there is also a solution that is guaranteed to pass. And the solution looks as follows: that keyword to Google, if you want to report about this, is the 0-1 principle. And the 0-1 principle is a slightly surprising result about these networks. And the result is such that if there is a counterexample, so an input that doesn't get sorted correctly by the network, you do not have to try n factorial possibilities, so all possible permutations. It is enough to try just 2 to the n different possibilities, because it turns out to be the case that whenever there is a counterexample, there is a counterexample that only uses zeros and ones. Intuitively, this is because, like, you can kind of highlight the place where the network sorts incorrectly. So if there is some place, some pair of wires that can be left unsorted, then you can put 0 on one of those wires and everywhere smaller, then put 1 on the other wires, and you will get the contradictions anyway. At this moment, I think I don't want to give you the full formal proof. If you look it up, for example, on Wikipedia, it's explained very nicely. And that is a pretty easy proof to follow. Just if you have any permutation, that is an example, the permutation has 2 values that will get sorted incorrectly, and then you choose different input values, which are ones and zeros based on those 2 values, and you will get another counterexample that only uses zeros and ones. So instead of trying a random subset of these permutations and hoping to get lucky, we can simply try all of the values 0 through 2 to the n minus 1 as combinations of bits. And additionally, this makes the solution very easy and short to implement, because the thing you can do is you can implement each of these operations using some bit magic only. So if you want to compare and swap 2 bits, you just extract them using some shifts and adds, and then compare them and build a new number. And if you want to sort a range, the thing you can do is you can extract the range, look at the population count, which is the number of ones within the number, and then you can just directly build the sorted range, which are just zeros and then ones, and place it back into the number. So each of these operations can be done in constant time using some bit magic, and this makes the solution very efficient. So you try 2 to the n possibilities, and for each of them you simulate a network, and you have a mathematical guarantee that the solution is correct. Either you discover a counterexample and output it, or when you try all of the possible inputs, there are just zeros and ones, and all the time in the world, and it certainly also works for other numerical inputs. Okay. Any questions about this one? Yeah. Good. Moving on. Okay, so the next question on the exam was the question of Fermat. A to the n plus b to the n equals c to the n n. Okay, so one of my major successes as a coach was that 2 years ago, like 2 months before the World Finals, I came to the conclusion that, all right, there have been enough tasks around the world that involve one particular technique that hasn't been used in the World Finals before. So it would be a good idea to let teams from our region train on this. So, like 2 months before the World Finals 2015, in one of the practice exams, I posed a question that was a slightly more difficult question on this particular technique. People from our region, from Czech Republic and Slovakia, got to solve it, and then the Czech team from Charles University went to get silver medal in the World Finals, and also almost had the first solve on the particular problem. They were only second because, second to solve it because they made a stupid mistake in the implementation at some point and to resubmit the solution. So I was pretty happy with correctly guessing that the time was right for this particular technique. But the technique I'm talking about is using the fast Fourier transform or discrete version of thereof in order to do convolutions and in order to do multiplications of big integers. So we will see very quickly what this is about. So we have a value of n, which is, in this case, up to 1 billion, I think. Yeah. So we are given n, which is between 3 and 10 to the 9, and we are given m, which is just below a quarter of a million. And now our task is to count the triples ABC, which are all non-zero, so they are from 1 to m minus 1 inclusive, with this particular property, that a to the n plus b to the n equals c to the n modulo n. So one thing we can do is we can actually go through all possible values of c. And for each value of c, we can compute the value c to the n modulo n. This can be done efficiently by repeated squaring. So there is this fast exponentiation algorithm. In order to compute c to the 16th, you just compute c to the 8th and multiply the result by itself. So this can be done very quickly. And what we will get will be a statistics for each possible remainder modulo m from 0 to m minus 1. We will get the number of different c that give these remainders. So we will try c equal 1. 1 to the n is 1, so it will be incremental 1 here. Then we will compute 2 to the n modulo n and increment the counter. And at some later point in time, minus 1 to the n modulo n can be again here. And in between, we got some results like this. So on the right-hand side of this equation, we know the number of possibilities for each remainder. And now we want to know the same information for the left-hand side, because the final answer is a sum where the remainder r goes through all possibilities, 0 through n minus 1. The number of left-hand sides with remainder r times the number of right-hand sides with remainder r. So we already know this for each value of r, and if we knew this, we could compute the final answer like this. So in order to have this equality, both sides have to have the same remainder. We try all possibilities for the remainder, and each time if we decide that the remainder is 7, we take how many different c's give remainder 7, and independently of choosing the c, we get to choose a pair A and B that give remainder 7. So each of these can be combined with each of these, we multiply those, and we add it together over all choices of r. So the only thing we need is this. So for each combination A and B, to know how many of those combinations give us each of these remainders. And now this is the only difficult part of this problem, because there are 250,000 choices of A, and independently 250,000 choices of B, and we cannot try just all possibilities A and B. Okay, so let's give this array a name, let's call it S. And now, let's take a look at the following polynomial. So there will be a polynomial px. Which will be the sum, where the r goes to 0 to n minus 1 of, and now this r times x to the r. So this is just a mathematical way to visualize this array. So we take this array in memory, we do nothing in program, we just look at this array to be the coefficients of a polynomial. So S0 is the coefficient at x to the 0, S1 is the coefficient at x to the 1, and so on. And now the main trick is a convolution. So let's take a look at what happens if we compute the square of this polynomial. In the square of this polynomial will be some new polynomial where r goes from 0 to 2m minus 2, and the new coefficients, let's call them p, so these will be pr times x to the r. And now, for example, the value t7 is what? This t7 is the coefficient with x to the 7 in the product. And the product, p, is one copy of the polynomial, so this is s0 plus s1 times x plus and so on. And another copy of the same polynomial, s0 plus s1 times x plus s2 times x squared, and so on. And if we want to get x to the 7 in the result, it can be done in multiple ways. So it can be x to the 0 here, multiplied by x to the 7 there, or 1 and 6, and so on, or 7 and 0. So this is s0 times s7 plus s1 times s6 plus and so on. So in mathematics, what we are doing here is called we are using generating functions, and by doing the product of the polynomial itself, we are essentially computing all possibilities how to combine two of those values, and we are already aggregating those choices into those buckets called T. So S7, for example, was the number of ways in which you choose one variable to get the remainder 7. And now T7 is precisely what we want. It's the number of ways in which we can choose two of the variables so that the remainders sum up to 7. So either we choose one variable that will give us the remainder 0, and the other will give us the remainder 7, or the first variable will give us the remainder 1, and the second one will give the remainder 6, and so on. So the sum of these possibilities is precisely the total number of ways in which to get the remainder 7. Or well, I'm deceiving you a small bit, because for example, if m equals 10, you can get the remainder r equals 4 also by choosing a that will give you a remainder 7, and b that will also give you a remainder 7, because 7 plus 7 is 14, and 14 modulo 10 is 4. So the last thing we will need to do is to take the terms e that will have values to m and over, and just add them below. So, for example, the number of pairs may be such that a to the c, a to the n plus b to the n modulo m equals r. The number of such pairs is p of r plus p of r plus m. So these are all the ways to choose a and b in such a way that the sum of the remainders is r, and these are all the ways to choose a and b such that the sum of these two remainders is r plus m, and those cover all the possibilities. So all we need to do in order to solve this task is to go from here to there. So to take the values s, the coefficients of this polynomial, and to compute the enumerary t, which are the coefficients of the polynomial multiplied by itself. And once we do so, then already we can do this. So this is pr plus ti plus m, this is sr, we multiply those two values, we sum it out and we have the answer. So this is the only conceptually and implementationally difficult step. There are some reasonably fast solutions which may have been fast enough to this problem. In particular, there is a technique called Karatsuba multiplication. Which is something reasonably easy to remember and be able to implement from scratch. But nowadays the trend is just to be safe, and if you are going to a regional or world finals in ICPC, the fast Fourier transform is something you should have in your team notebook, and you have a tested trial implementation to just rewrite into your program. So there is a technique called FFT, which is based on like square roots or nth roots of unity in some fields, either in complex numbers or in some finite field with lower prime. And you can use this to multiply things very quickly. So we can actually, as long as everything fits into machine work, we could go from here to there in n log n time. This would be n to something like 1.57. This is just an log n if you do it using FFT. Okay, yeah.
Is there any specific reason why m is greater than 47, greater or equal than 47? Because we were brewing to try to find some pattern, and we saw that it worked for smaller m's. We found it really weird that m is greater or equal to 47.
Yeah, there was no specific reason for that. I just had to choose a lower bound, for example, n equals 2 may behave weirdly for some solutions, and I just wanted to choose an lower bound that would be really large enough for there to be no special cases. And 47 is a favorite number of mine. Like 47 is the quintessential random number. It occurs in nature very frequently. If you pay attention, you'll certainly notice many occurrences of 47. There used to be a website called 47 Society, which is a club for people who track the occurrences of this number. So, in addition to 42 being the answer to life, because everything, 47 is also a very important constant of the universe. Yeah?
I could not understand why the T of R plus M.
Yeah. So let me again give you an example. So that let's have a very specific example. So let's say that m equals 100. And now you know that, for example, S30 is the number of ways in which you can choose A and get the A to the n will give the remainder 30, right? S75 is the number of ways to choose, for example, B, such that the remainder of B to the n modulo m will be 75. And now when you do this multiplication, these two terms, S30 times S75, will contribute to the power of x to 105. So in t to the t squared of x, t 105 equals something plus s to the 30 times s to the 75 plus and so on. So this particular combination of values will contribute to having the remainder 105 when you choose this particular pair A and B. But we don't have the remainder 105 because we have m equals to 100. So this should be 5. But if we do this like just a proper multiplication, we will get some of the combinations at 5. So for example, if A gave remainder 2 and B gave remainder 3, we will get it there. But in some cases like this, 30 and 75, we'll get it here. We need to add those possibilities together. So these are the ones where it doesn't overflow, these are the ones where it does overflow.
Yes. There are many brute force solutions, like a squared divided by some constant that work.
Not that I'm aware of. And then there were two, so we are left with two problems. Alright, and the next problem is called the minimum spanning forest. So, for this problem, what we are given is a weighted graph. And we are describing a process that consists of two stages. In the first stage, for each edge of the graph, we flip a coin, and based on the flip, we either keep the edge or erase the edge. In the second step, we then compute the minimum spanning forest of the graph. So this would be the minimum spanning tree, but the graph is not necessarily connected. And the question is to compute the expected cost of the minimum spanning tree. Now the first thing to know in problems that involve probability and expected values is an important property called linearity of expectation. If you have a result that is the sum of multiple variables, multiple random variables, the expected value of the sum is always the sum of the expected values of those individual variables. And this is true regardless of whether the variables are independent or not. So there can even be dependencies between those variables. The result is always a sum of those expectations. So to visualize this, if you roll two dice and you want to have the expected value of the result, is the expected value of the result of one die plus the expected result of the other die. If you roll one die and then set another die to the same value, the expected the value of the result is still the expected result of what you see on the first die plus the expected result of what you see on the second die, if they have the same number of sides at first. And this seems to be a very simple property, but it can often be used to solve very complicated problems very easily. A favorite example of mine for linearity of expectation goes as follows. So imagine that a ship has landed in harbor, and all of the sailors have leave to go to the shore and get drunk. So there's a ship. On the ship there are some quarters where the sailors live. The quarters are numbered 1 through n. The sailors are also numbered 1 through n. They go to the shore, they get drunk, and when they go back, each sailor being drunk just chooses a room uniformly at random and crashes there. Even if there are already some people sleeping there, he just adds himself to the pile and sleeps off the drunk state. And the question now is, what is the expected number of sailors who wake up in their own cabin? Now, you can treat this as a combinatorial problem. You can treat it like a sum over all possible n to the n choices of sailors. You can compute what is the number of choices such that exactly k sailors are in their own quarters and the remaining ones are not. Then you will get a sum with some exponentials and so on. And if you can then bash some mathematics in the sum and to get a closed form solution. Or you can use linearity of expectation. For each of the sailors, the probability that the sailor will sleep in his own cabin is exactly 1 over n. Which means that the expected number of nights the sailor will spend in his own cabin is 1 over n. If we did the same experiment n times over, the expected number of times the sailor will be in his own cabin will be 1. So for each sailor, the expected number of times he sleeps in his own cabin is 1 over n. And as there are n sailors, we can add it together and we get the answer of 1. So it's a very easy way to solve this task. And something similar is going on also in this minimum spanning tree forest problem. The answer can simply be computed by summing over all edges, because each edge is for each edge we can have a random variable, how much it contributes to the minimum spanning forest. And this is either its weight or 0. And its weight, it is with probability that this edge is selected to be in the minimum spanning forest. So what we need to do is for each edge, we need to essentially compute the probability that we will include it. And the result is then the sum over all edges, the probability that the minimum spanning forest contains this edge, times the weight of this edge. And how do we do this? Well, we can imagine running minimum spanning tree or minimum spanning forest algorithm on all possible instances at once. So the best algorithm to choose here is Kruskal's algorithm. Kruskal's algorithm works as follows. We sort the edges from the cheapest one to the most expensive one, and then in this order we add them. So at the beginning we have just n discrete vertices, there are no edges, and now we are processing edges starting from the cheapest one, and each time we get a new edge, we take a look at the two vertices it connects, and if they are already connected by cheaper edges, then we discard the edge, and if they are different components, we then add the edge. So essentially we are doing the union fancy algorithm and merging components into larger ones as we go along. So at the beginning, there's only one possible state. With probability 1, the state are 4 discrete vertices. Now we come to this edge. And there are two possible cases, each has a probability 50%. Either this edge is present or this edge is absent. If this edge is absent, we remain in this state. If this edge is present, we use it and we go to this state, which is the state that these two vertices are already in the connected component and these two are not. Now we go to the second edge. So we know that the probability that we are in this state is 0.5, the probability that we are in this state is 0.5. And now in each of them, we can repeat the same process. So we have a new edge, either it is there or not. So after we process the second edge, we will have only 4 possible states. One of them will be the discrete state with possibility 0.25. One of them will be state that looks like this, with possibility 0.25. One of them will be a state that looks like this. Again, 0.25 and 0.25. The case looks like this. And now comes an optimization. For a case that looks like this, we don't have to remember that we have these two particular edges. All the information we need is that this is a connected component, and this is a connected component. So all of the states will have the same connecting components. After each step of the algorithm can be merged into one. So essentially what we do, after we add a new edge into a component, we do the transitive closure. So we compute all of the other edges that could be there, and we can directly add them. So it's very easy to represent the graph just as a vector of bits, saying which edges are present or not, and after each iteration just run one for one, showing something to do the transitive closure. So these are the 4 possible states after we process this edge. And now when we go to process this edge, again from this state we will get 2 new ones, from this state we will get 2 new ones, from this state we will get 2 new ones, but these ones, if we have the edge here, and if we have the edge here, both of them will lead to the same state that looks like this one, because again, these 2 vertices already form the connected component. And in this particular case, both of the branches, either adding this edge, so for this edge, both of the cases will lead to the same state, and in neither of them we add this edge because these vertices were already connected. So for this particular edge, what we will get is that from this state, we would use it with probability 50%. So 0.25 times 50 times 0.5 of using this edge. Here again, in this state, we would use it with probability 50%. In this state, we would use it with probability 50%. But in this state, we would never use this edge. So for this particular edge, the probability of it being used is only the sum of these probabilities times 0.5. So this is the entire solution. We are processing the edges one at a time, and each time we remember the set of all possible states we could be in, so set of all possibilities, how the previous vertices can be divided into connected components, and for each of them we have the probability of being in this state. And using this information we can now take the new edge, compute the probability that this edge will be added to the minimum span first. In some cases it will, in some cases it won't, and also compute the new probabilities and the new states after this edge is added. So the main source of efficiency, if we can call it that, in this solution, as opposed to the brute force solution, is if you wanted to solve this problem by brute force, you need to consider all possible subsets of edges. So if there are 10 vertices, there are up to 45 edges, and those 45 edges have 2 to the 45 subsets, which is too much. But in this solution, the states are only the equivalence relations on the vertices. So the ways to divide the vertices into connected components. And this is a value that does grow exponentially, but much, much slower. So the actual number of valid reachable states for n vertices will be only exponential with a small constant in the number of vertices, not in the number of edges. And this, for n equal 10, still very conveniently fits into memory. So the actual solution is very fast. It should be summed even just 100 a second, not 10 a second, but possibly.
After each time we add an edge, we have to compute the transitive closure.
Yes. Yeah, you can afford this. Well, one of the implementational details what I did in my solution is that as there are only 45 edges, and you just need the information whether or not an edge is present in the graph. So what you can do, you can simply take the graph and encode these 45 bits into long blocks. So each of the possible states is just a 45-bit integer. And each time you get a state, you like unpack it. So you look at the 45 bits, you fill in the 10 by 10 adjacency matrix. Then you look at the new edge, you are ready or not. And then after you add the new edge, you run for Warshawk on this graph with 10 vertices to compute the new bits, and then you call it and pack them again into a long and store it into a cache somewhere.
Mas, ó, we may also calculate the minimum spending first iteratively but the list of this move set, and for every edge we take, we remove from the move set, and if you remove another edge, you remove from the move set again, and but I did not elaboration on this approach, but I believe it's a way to calculate faster the minimum spending forest. I don't know.
I'm not sure what you mean now. It might be possible to also have other approaches, like there are other spanning tree algorithms that Cruz calls, and they should also be possible to adapt them to count this. So you can instead of processing the edges one at a time, you can start from a state where just this vertex is the minimum spanning forest, and then you are growing it one edge at a time. But I think the complexity in the end will be the same. So I don't know a way of solving this task in polynomial time, and I assume it doesn't exist. So I think it will be exponential.
Is there like a closed formula for the number of partitions?
Yes.
It's like because we tried to find it, but we didn't. We just used
it. There is. I don't think there is a nice closed form formula in the sense that it would be answering something, but there's something. But there is, for example, a very simple like recurrent relation that you use.
Yes.
A very good resource for this, especially if you have internet access. The content online encyclopedia of integer sequences. You just plug in the name, so in this case you can say integer partitions or exponential relations, and you should be able to find that sequence. Or you can just brute force compute the first values and it will give you also the information about formulas and these values. So for example, if I will be solving an online round of code forces and I encounter these and I want to know whether it's fast enough, and I look it up on online encyclopedia or Wikipedia, math world to see what is the actual value of the number of partitions for my maximum n. And if I see that it is only 300, then I'm very happy.
The basic here was like equivalence on graphs that have the same minimum spanning forest, right?
Yeah.
But I did not understood, like, I didn't understand how you do that.
Imagine that you actually try all possibilities. So there are 2 to the number of edges possibilities for the input graph, and on each of them you will run Kruskal's algorithm. And at the end, during the algorithm, you will add some edges to the minimum spanning forest, and you will discard some of the edges, and you can compute the sum of those edges you add. And at the end, you will take the result, and you will multiply it by 1 over 2 to the n. And you will do this for each possible branch, and you will get the answer. And the optimization I'm doing now is that during this process, we are repeating the same computation many times. And the same computation is that if in one of the branches, you added an edge like this, and you added an edge like this, and in another branch, you added an edge like this, so these are the same two vertices in the graph, And now we are going to process the remainder. So for each of the possible combinations of the remaining entries, whatever you do in this graph, you'll have the exact same result in this graph. So you can view the entire computation as a process of memorization. So this first time, I actually evaluate all the possible branches and sum up the answers. And this time, I look it up in memory. So I have already had this situation when this was a connected component and so on. And for this situation, I know what is the sum of all the possible answers for the possible probabilities. And it can also actually be implemented in this way, as this kind of recursive memorization. But the other implementation I described, was the same thing, but like dynamic programming. So what you do is you start at the beginning with the disjoint graph, and you are actually, as if you were doing all of these 2 to the n possible computations in parallel, and only after each iteration, you merge together the states that are equivalent.
Eu preciso fazer para que ver se eu posso calcular. Então você tem que calcular. Mas eu acho que você pode já.
Alright, one final problem left.
A cada bitmestre já deixa a bitmestre isso. Vou fazer o mapa de bitmestre.
The final problem from yesterday is a problem about positive and negative subsequences.
Os primeiros 10 minutos eu escutei o Arthur falando. Gostei desse problema.
Alright, so the main idea for this problem is actually quite a traditional mathematical puzzle that has been used, I think, in the 70s or 80s as an IMO problem. So this was a hard problem in the International Mathematical Olympiad. But it's only hard because most mathematicians don't know what they're doing. We as a computer scientists are better equipped to deal with problems like this one. So we propose as a program from this problem, it's easier to solve. So the story in this problem is that we have an unknown sequence of integers, and we are given some information about this sequence. For example, the sum of any 3 consecutive elements is strictly positive. And the sum of any 5 consecutive elements is strictly negative, and the sum of any 7 consecutive elements again is strictly positive. So we are given a collection of information like this. Each of these values is up to 1000. And the question is to determine whether there is an infinitely long sequence with these properties, or whether all the sequences are finite, and if they are finite, to find one example of the longest possible sequence. Okay, so let's start with some easy cases. First of all, if all of the constraints tell us that the sum of some range has to be positive, then it's very easy. We can have an infinite sequence of ones, and everything is true. Also, if all of the constraints tells us that the sum of some range has to be negative, and of all of them say negative, 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 again we can have an infinite sequence of minus ones and everything works. On the other hand, as soon as you have at least one information of each type, there has to be an upper bound. Why is this the case? Well, because if you have the sum of any 3 consecutive elements is positive, and any 5 is negative, you can take a sequence of 3 times 5, and what you get is either a sequence that can be divided into 5 groups of 3, or you can take the same sequence and divide it into 3 groups of 5. And now this has to be positive in each group, so the entire sum has to be positive, but at the same time the whole sum has to be negative, which is a contradiction. So whenever you have 2 informations that some range has to be always positive, some range has to be always negative, the product of these is an upper bound of the length of the sequence. So now the question is, if we already know that the answer is finite, how do we find the maximum? One other important property we can realize is that if you take a valid sequence and you remove the last element, you will still have a valid sequence. Because all of these ranges have the correct property, all of these ranges have the correct property. You just removed some of those ranges. So removing elements does preserve the correctness of sequence. What this means is that there is some kind of a threshold. Starting at 0 and ending at some length, the sequence will still exist. And from this length plus 1 to infinity, the sequence doesn't exist. So the answer is somehow monotonous. And one of the good ideas, whenever we have some property that is monotonous, is that you can binary search for the correct answer. You can take some particular value and ask a question, is there a sequence of this fixed length? And this question may sometimes be easier to answer than the general question, what is the optimal length? So instead of solving an optimization problem, which is the maximum length of the sequence, if we know that the property is monotonous, we can binary search for the answer, and we can answer an easier question, which is just yes-no question, existence question. Is there a sequence of this length? So what does change for us if we fix the length L of the sequence? So we have some values A1 through or let's go like 0 to L minus 1. What we have here is some information about sums of a range in this array. And this is why I'm talking about us computer scientists being better prepared to deal with such problems than the mathematicians. Because for mathematicians, a sum of a range of an array is something that they don't encounter so frequently. For us, this is a very easy thing because we know how the sums of ranges work. We want to say what is the sum of these elements and we want to do it quickly. What do? You pre-compute the prefix sums, and then the prefix sum from the start to here minus the prefix sum from the start to there is the sum of this range in constant time. And this is exactly the tool we need now. So in order to talk about sums of ranges, we need to look at prefix sums of the original sequence. So given the original sequence A, we can now define Si to be the sum over j less than I of Aj. In other words, S0 is the sum of the first 0 elements all the way through SL being the sum of the entire sequence. And we know that, so this is the original sequence, now the sequence S is one element longer, it starts with a 0, continues 0 plus A0 is A0, A0 plus this is the next value, plus this is the next value, and so on. This value plus A0 minus 1 is the sum of the entire sequence. And now from each of these constraints, what does it tell us? The constraint that the sum of any 3 consecutive elements is positive tells us the following inequalities. A3 minus A0 is positive. A4 minus A1 is positive, and so on. In other words, A3 is greater than A0, A4 is greater than A1, and so on. This other constraint with 5 will also give us some inequalities, starting with A5 is less than A0, A6, or sorry, this should be S's, not A's. Also here, all of these are the prefix sums. The sum of the first 5 elements is less than the sum of the first 0 elements. The sum of the first 6 is less than the sum of the first 1, and so on. Now this is all the information we need because we can visualize all of these informations as directed edges in a graph. And if this graph happens to be acyclic, then everything is in order. And the topological order of these vertices of the graph is actually one possible way of assigning values to these S's. So we find the smallest one, we give it 0, we find the second smallest, we give it 1, and so on. And you have a valid solution. On the other hand, if the graph contains a cycle, so this one should be greater than that one should be greater than the other one, and the other one should be greater than this one, there is a cycle, the cycle is a contradiction. So if we find a cycle, then there is no solution. So this is the entire algorithm. binary search L. If you fix L, construct this set of constraints, determine whether there is a cycle or not. If there is a cycle, your L is too large. If there is no cycle, you can actually find valid values for those SEs, and once you have those, you can then compute the original arrays with this minus this is this minus this is that, and so on. And this will give you the optimal example. Alright, so that's it for yesterday's problem set. What's the time? 11:15. Okay, so let's take a 10-minute break and then we'll spend the last half an hour before lunch discussing something else.
Nossa, cara,
não preciso fazer nada, é ótimo. Só fala pro Carlinhos, o Carlinhos tá assistindo ele grava. E aí, Carlinhos, Carlinhos, a gente vai mudar o nome do vídeo daqui a pouco. Você sabe? Espero que não precisa. Mas a gente tem que passar confiança. Como que não sabe de tudo. Por isso que eu não. Eu só apertei start no Android e não funciona. Ah, é? Computação é um negócio difícil. Grande porn mode.
Não, você não me falou, porra. Soma de
fazer uma série se eu sou uma você tem que refazer.
Muito bom isso.
Sabe quando eu montei as provas?
É porque exponencialmente Não, pode ter os três, pode ter 2 e 1, pode ser esses 2 e 1, pode ter esses 2 e 1.
Todos os possíveis estações não saem. acontecer agora. Aí a gente viu que na prática
Você tem uma bola e você tira pra cá pra direita da vazia. Tira uma bola, tira um quadrante. E aí você escolhia
ah, sei.
era infinito, né? Você consegue eliminar sempre diagonal.
E aí, infinitamente, mas ficava sobrando um caminho aqui, eu não ia tirar aqui. Você conseguiu tirar aquela terceira? Assim? Isso faz
This time it's much easier because this time you just so the way the promotion is just divided by so the corner is one, the next already with 1-4 it will just so it's just a big noise.
É porque eu tenho que ficar fazendo nada, você não vai
Dá pra chegar até lá. A bola aqui, botar ela aqui. Se eu quiser, de uma maneira.
Already if you have just two values, so for A it has to be positive, for B it has to be positive. For this, you will already strength the maximum length of the sequence is only A plus B minus I think the greatest. So if A and B are relatively prime, it's A plus B minus 1. So you don't have to go up to the product. Your verification happens on this large constant vector and then you can just there is a mechanism to do and worse.
Então, também a ideia
So this may be either the first, so it must be is either the next
também tem interesse nesse nosso trabalho assim possível.
Yeah.
Faz sentido. Então,
Considerando que tem 10 coisas diferentes. Então, se você mudar o nome dessa coisa, não vai diferença. Você na ordem, você vai
Como que conta isso? Qual que é o número certo para isso? Sabe? Ah, é?
Quer dizer, tem uma forma que tem uma isso não é difícil, só que não dá uma boa definição. Não. Recorrência é.
Teve um presente da Dilminha para todas as meninas que participaram da prova. Todas as meninas participaram da prova. É da mulher do apartamento do Texas lá.
Essa é a forma.
É o horário de mulheres adultas. Nossa, que gozado.
Imagina você coloca uma dessa
Eu ganhei presentes que a Dilminha mandou para todas as mulheres que iam participar do campo. Sabe? Todas as mulheres. Todas as mulheres. Assim, a melhor mulher que começou a melhor. Exatamente. O bom é que ele tinha esse tipo, passa pra mulher que passar mais problemas do que o passado. Pra mim, você tem que passar pra mulher, você passa pra mulher. Se for 16,0, você
Você pega um cara que tem as coisas assim, você não passar, você vai pegar o cara, acabou de usar o cara dele.
Você quer que eu marasse no
Pega a cor do cara.
Eu não sei por que mais. I guess I should try. I'm going to computer science. It's a common trade.
Alright guys, check it out and let's continue in a minute.
Deixa eu ver qual.
Pede para todas as mulheres do campo.
a big, like a small topic to talk about, and I'll try to tell you a little bit about randomness, why it can be useful, and what you need to know about it in programming conditions. It turns out to be the case that in many cases, making a random choice can be used to speed up algorithms very significantly. There are many questions of the type, verify whether a property is true or false, and if it is false, what you are looking for is a counterexample, in other words, a witness that the property doesn't hold. And it can often be the case that the number of witnesses is large, but their distribution is somehow unknown, and we cannot give any guarantees if you for a witness sequentially how long it will take. And looking for one randomly can be very efficient. So let me illustrate this with a very simple example. So suppose that you have a, let's say, DVD, so some kind of a physical medium with some information. So you have 4.7 gigabytes of data, or maybe in bits, this is this type 8, so it's 32, and let's say it's approximately 3.7 times 10 to the 10 bits, something like this, or let's maybe round it upwards, 4 times 10 to 10 bits. Okay. We have a lot of bits. Now your friend at the other side of the world has also bought the same DVD, or so he thinks. So now we have person A with the DVD, a long sequence of bits. We have person B with the DVD, and they want to compare those contents. So they want to compare whether this string of bits is exactly equal to that string of bits. Now, even if we assume that they have a communication line with zero error, so they can communicate directly and transfer all the bits without making any errors during the transmission, it will still require a lot of communication to be completely sure that those two sequences are exactly the same. Well, one obvious solution would be that person A will send the content of the entire DVD to person B, and person B is comparing one bit at a time. And this is the best you can do. Even if you are allowed to go back and forth between those two people, there is no better deterministic solution. The minimum amount of bits you need to transfer is this, let's call it n. So if you have n bits here and n bits there, if you want to be 100% sure that those two sequences are correct, you need to transfer n bits or more. This is actually very easy to prove mathematically. So let's fix the sequence A. And now for each possible, if we had a better algorithm that always uses fewer than n bits, then we can fix the sequence A, take a look at all possible sequences B, and for each of them look at the communication that took place, the vector of bits that exchange places. And now if we always use fewer than n bits, then there have to be two different sequences B that correspond to the same communication. And it could be the case that one of them is correct, one of them is wrong, and then you cannot tell those apart. The person cannot be sure whether B has one of those sequences or the other. Well, the easiest way, if we were just doing this with one-way communication, is very obvious. If you send the same sequence of bits for two different sequences, then person B cannot tell which of those two is your component. So in order to be completely certain, the communication complexity needed is n bits, so 4 times 10 to the 10 bits. You need to transfer some 40 billions of bits through the network. But with a probabilistic approach of randomization, we can get a much better practical solution. So one thing you can do now is you can imagine that this A and B, the sequences of bits, are simply two very large numbers written in binary. So A
is actually sum where I goes from 0 to n minus 1, ai times 2 to the I, and the same for b. And now, our algorithm will be very simple. I will fill in the details later, but the outline will look as follows. A chooses so this, let me write it in. So A in the box is the person, and just the A is the value of the number. So the person A chooses a random prime P. Person A computes the number A modulo P. Person A sends to person B a message consisting of this value A modulo T and P itself. Person B computes B modulo P and compares it. So what happens with this protocol? If those values A and B are indeed the same, and regardless of this random choice, the remainders will definitely be the same. So if the numbers are correct, then this protocol does accept it as correct always. So there is no mistake in this case. If the numbers are different, we may discover this by getting different remainders, but we may also be unlucky. We may be unlucky that we happen to choose such a prime P that the A and B are different, but the remainders turn out to be the same. So this algorithm is not always correct. It can sometimes make a mistake. Sometimes it can be the case that A and B are different, but we don't discover it because we chose an incorrect prime P. So now let's take a look at what it means for a prime to be incorrect. So we will suppose that A is not equal to B, so this is the interesting case. But A gives the same reminder and then there's B modulo P. In other words, we can rewrite this that P divides the difference A minus B, or the absolute value there. Now what's going on here? This absolute value of A minus B is one specific number. The number, so this had n bits, this had n bits, so the difference also has roughly n bits. So this is an n-bit number, and the only, so if P has this property, it means that P is one of the bad primes, one of the primes we don't want to choose, because A and B are different, but this particular prime P doesn't show it. So every bad prime P has to be a divisor of this particular number. So this means that among all of the primes, which is an infinite set of values, there are only finitely many of those bad P's. The bad P's are only the divisors of this value and nothing else. So infinitely many primes in general, and only a small finite set of counterexamples of the bad primes you don't want to choose. So in order to make this algorithm work with high probability, all we need to do is to choose a prime P from a set that is large enough. And if we choose P from a large enough set, we will have the certainty that in the set there is much more good primes than bad primes. And this will give us very high probability of a success. So, how many bad primes can there be? And this is an n-bit number. We know that A minus B is less than 2 to the n, which is 2 times 2 times 2 n times. And now we write a specific prime factorization of this number. it will be a prime times a prime times a prime, and so on. And each of those primes is at least 2. So the number of different primes in the prime factorization of this number has to be less than n. So among all of the primes, there is a small group of bad primes, and there is less than n of those. So in our case, the number of bad primes is less than something like this, 4 times 10 to the 10. We could actually compute an even stricter upper bound than that, but we don't have to. So now what we can do is we can take a random prime from, for example, a range like this. A range from 1 to n squared, a range from 1 to n squared times log n if you want to. And in this range, it can be shown that the problem, so the number of, well, let's do it like this. So this will be n squared log n will be the upper bound for the prime we're choosing. And within this range, there are roughly n squared different primes. Out of those n squared primes, at most n are bad. So the probability of choosing a good prime is roughly n minus 1 over n. On the probability of choosing a bad prime equal to 1 over n. And then we do this entire protocol. And one good thing about this is that for the constraints we listed there, this p should fit barely, but should, into a 64-bit integer. So the entire communication here is we are sending 2 64-bit integers, 128 bits, and already the probability of giving the correct answer is greater than 1 minus 1 divided by n, which is greater than 1 minus 1 divided by n to the 10 or something like this. In other words, the probability that we will make a mistake because 2 files are different, and we will claim that they are the same because we were so unlucky to choose one of the bad primes, the probability of this happening is only roughly 1 over n, 1 over 10 billion. And if this is not low enough for you, what you can do is you can repeat the same process 5 more times. After 6 repetitions, and each time choosing a different random prime independently, the probability that you will make an error in all 6 runs is less than 1 over 10 to the 60. And already we are at the level of probabilities you will never see happen. Like literally, if you have a computer on one side of the world, a computer on the other side of the world, and a network between them, the probability that during the execution of this algorithm, some part of this will be destroyed by the meteorite is much higher than 1 over 10 to 60. So at this point in time, the probability of a hardware error is much larger than the probability of a software error with such a probabilistic algorithm. And you are still sending less than a kilobyte of data to compare the left-hand side and the right-hand side. So this is the difference between a deterministic solution and randomization. This is what randomization can bring you. In order to deterministically show that with certainty those 2 files are equal, we need to transfer billions of bits. In order to probabilistically convince ourselves that they are equal, we only need a kilobyte of data with some random choices. So this is the whole difference in the game. There are some countries, if the files A and B are different, there are some counterexamples, there are some primes that show the difference. Actually, almost all of the primes will show the difference. But still, finding one deterministically is hard. You cannot do it. You can only do it probabilistically. And observations like this matter also in the design of algorithms many times. You will have many cases in which a probabilistic algorithm is very efficient and we don't know a way of doing the same efficiency deterministically.
Of course, many of the problems with this property are in some sense related to the prime numbers. This is because, well, the distribution of prime numbers is something exactly the property I was talking about. The distribution of prime numbers is somehow chaotic. We don't know enough about it to describe it nicely, and we're looking for a prime with some specific properties. Often it's hard to do so. So, in particular, one of the examples where randomness is known to help is primality testing as such. So you have a number, you want to test whether or not it is a prime. Whether if it is a composite, you can find a witness, a divisor. If it's prime, you have to find a witness of a different kind to prove that it's prime. For a long time, we didn't know whether this primality testing is even possible to do deterministically in polynomial time. And it was a famous result some decades ago. The primes actually is in P. There is the Indian algorithm that shows that how to compute this in number of digits to the power of 6 deterministically. But there are more efficient, practically used probabilistic primality tests. The canonical one that is mostly used is the Miller-Rabin probability test, which uses some properties from number theory and just does like a random choice here and an exponentiation there, comparison. And if it worked out, then we claim it is a prime. If it didn't, we are certain that it's composite. So it's the same game over and over again. So one way of using randomness in algorithms is like this. When we are searching for something, we know that there are many ways to find it, like there are many ways to find the proof that the number is composite. But we don't know anything about the structure, we don't know enough to argue about it. And then we can just look for those witnesses randomly and test for them. And this is what's happening in many algorithms. But there are also other ways for randomness to help us. There are algorithms that are always correct, and the running time only depends on whether we are lucky or unlucky with our random choices. The canonical example of the second type would be, for example, quicksort. In quicksort, you can do a randomized version in which you choose the pivot randomly, and then you reorder the array into smaller values, the pivot into larger values. And if you are really unlucky, you will get a quadratic running time. But this shouldn't happen. With high probability, your choices of pivot should be good enough, because like if you hit anything within the middle 80% of the array, you will cut off a significant part of elements on either side. So almost all of the choices in each iteration are reasonably good. And if you do the choice at random, you are guaranteed that with high probability you will hit a good choice reasonably frequently enough. So there are mathematical results known for decades that with high probability the running time of randomized quicksort is actually always n-log-n. You will never see those special cases with close to zero probability when quicksort will be running significantly longer. And it also matters when it comes to hashing. If you have hashing is a game that you have elements and you want to place them into arrays somehow uniformly. So you just magically guess a big hashing function that will distribute those elements of yours, and you hope for a small number of collisions. But even if you are distributing the elements completely at random, collisions are still something that is happening, and this is something computer scientists should know when they are designing an algorithm like this or using a hash table. It is good to know how hashing actually works and what to expect from these collisions. One very famous mathematical property related to these collisions is the so-called birthday paradox. A birthday paradox is not a paradox as such, because it is an actual mathematical fact. It's just that the fact is unintuitive, and that's why it got this name. The paradox is about the following problem. So imagine you have a room full of people, such as this one here. So now there are two possibilities. One possibility is that each person in this room was born on a different day of the year. So each of us has birthday on a different day. The other possibility would be that two people in this room share a birthday.
And now the question is, depending on the number of people, which of these two options is more likely? Should you, if you see a room with 30 people, should you bet on all people having different birthdays, or should you bet on 2 people sharing the same birthday? And now for many people who didn't encounter this problem before, the intuition is as follows, that there are 365 days in a year, disregarding the leap years and the 29th of February, so 365 days. So the answer, the threshold should be somewhere around the half of this number, right? If we have 180 people, then we should already have probably some collisions, but if we have fewer than that, then probably not. And it turns out to be the case that the threshold is much, much lower. In fact, for this room, let me see, 7, 14, 19, 20, 30. Yeah, we should be very likely to have 2 people share the same birthday. As you go to lunch, you can discuss among yourselves whether we actually do have such people, but it turns out to be that the threshold is already n equal to 23. So already if you have 23 or more people in the room, you should bet on 2 of them sharing the same birthday. This can actually be worked out mathematically quite easily, because imagine that you forced all of the people out of the room, and now you are letting them enter one at a time. And each time you are computing the probability that still nobody shares the same birthday. So, given the assumption that the birthdays are distributed uniformly, which in fact isn't true, and this contributes to this number being even lower in practice, but if they were distributed uniformly, what's happening? When the first person enters the room, it's completely certain that there is no collision within the room. There is just a single person, and regardless of which day they are born on, with probability 1, there is no collision. Now we have a second person entering the room, and the probability that they have a different birthday than the first person is 364 divided by 365. And if this happens successfully, now we call the third person, and we already have 2 people with different birthdays in the room. So the probability that the third person will be born on a yet different day is 363 divided by 365. And we can go on like this. We can just take a calculator, keep on multiplying, and we will see that after 23 iterations, this probability will go below 0.5. So you see a room with 23 or more people, you should already bet on there being a collision, of there being 2 people with the same birthday. This can be generalized also to other planets, which have D days instead of just 365. And the threshold should be approximately, if my memory serves me right, it should be approximately square root of 2e. It's certainly on the order of square root of d. I'm not sure about the constant right now, but square root of 2d is, I think, my best guess at the moment. So what this means for us? This problem about birthdays is actually the same problem we have when we are doing hashing. So for example, if you have a hash table of size d, even if you had a really perfect hash function, even if the hash function was distributing the elements as if they were random, as soon as you are distributing more than this many elements into the array, you should expect a collision. So if you have an array of size 1 million, and you are storing 1,500 elements into the array will still be very, very sparse. There will be lots of empty spaces, just maybe 1 or 2,000 elements into 1 million size array. So it's still very sparse, but already you should expect some collisions. So collisions in hashing are something that cannot be reasonably avoided. You cannot afford to spend so much memory. So if you are using hashing as a data structure, collisions are something that will always be present, and you have to come up with a strategy of handling those collisions. There are also other uses for hashing, and one very popular one is that hashing can be used to solve many string problems. For string algorithms in stringology, there are many exact algorithms. For example, we have the Kluth-Moritz-Pratt substring search, which is deterministic and runs in linear time. But there are also randomized solutions based on hashing, like the rabbit card approach, which is you take a fingerprint of a string, a hash of the string as if it were a large number, modulo some randomly chosen prime, and then you compare two strings for equality in constant time by just comparing those hashes and hoping you don't hit a collision. And this is where the birthday paradox comes into play. Because, for example, suppose that we are solving a problem like this. This is a long string H called the haystack, and the length of H is lowercase h. And then we are looking for a substring called needle, and the length of the needle is n. Now, if you want to do this with hashing, what you will be doing is you will be taking the hash value of this needle, and you will be comparing it to many different hashes of these values. And you don't want to have a collision there. Or maybe if you, wow, okay, this is not the best example. Let's take slightly different one. So let's take a problem that looks like this. You are just given a single string. You are given a constant k, and your task is to take the substrings of that k and see how many different substrings are there. This can be solved using hashing by simply computing the hashes all of the substrings, inserting the hashes into a set, which discards duplicates, and then looking at the size of the set. Of course, if you hit any collision, you will get an incorrect answer because you will take two different strings and you will hash them to the same value, so it will appear as if they were the same string, but they are not. So in order to use the hashing algorithm for such a string and get a correct answer, you need to make sure there will be no collisions. And this is where birthday paradox comes into play. If you know the length of the string, h, then this is roughly the number of different strings you will be hashing. And each of them will get a number as its hash value, and you want to make sure there are no collisions, or make reasonably certain there are no collisions. And you know that if you are hashing into an array of size d, and you exceed this threshold, you will already start to see collisions with high probability. This means that if you are hashing h values, the range of your hash function should be significantly greater than h squared. So for example, if h is 10 to the 6, this would be a normal constraint in the program of this problem. You have a string of 1 million characters, then your hash function should return values which are at least 10 to the 12, and preferably even larger. Because if you will be returning smaller values, then you are taking 10 to the 6 different strings, and you are as if placing them into a hash table, which has a size smaller than 10 to the 12. And from the birthday paradox, we already know that there will be some collisions occurring. So this is something you don't want to have. So the trick here is to be reasonably certain you will not get any collisions, and this simple probabilistic solution actually works in a contest. You need to make sure that the range of values is large enough. So in this case, the thing I would do is I would probably choose two separate random primes, each of them roughly equal to 10 to the 9. So P and Q are approximately 10 to the 9. And then I will compute one hash function modulo P, another hash function modulo Q, and concatenate those two values to get a value that is up to 10 to the 18, or just compare each of them separately. Why do I do this like this in two steps? If you choose a prime that is up to 10 to the 9, then you can do all of the computations in 64-bit integers easily, because if you multiply the values that are up to 10 to the 9, it still fits into a long, into a 64-bit integer. So if you choose a prime that is 10 to the 9, you will not get enough values from a single prime, but you will get an easy way to do the computations. And you can do the same thing twice. This is just a cycle program with 2 different primes, and suddenly you have a hash value that has a range of 10 to the 18. And if you take 10 to the 6 different objects and hash them into an area of size 10 to the 18, you shouldn't see any collisions. So the probability of seeing the random collision should be very low. So this is a good choice of constants. And by knowing the birthday paradox, by knowing the underlying mathematics, I know that this choice of constants is good enough for the problem. I have to be really, really unlucky to fail with such a solution. Of course, let me conclude today's lecture with an actual true story from the practice, which is during some code forces round, there was a problem with stringology, and there was a contestant who submitted a solution like this, and hardwired the constants p and q to be 10 to the 9 plus 7 and 10 to the 9 plus 9, which are the 2 favorite primes of every contestant. And what happened, of course, a few minutes later the solution was hacked. So the person was like, well, okay. Then I see what happened. The other person read my code and noticed that the fixed primes are bad because they can find a counterexample that just breaks these 2 primes. And so I should choose the primes at random. So they implemented a new part of code, submitted it with choosing the primes at random. So P was called the rand function until it hit the prime, and called the rand function again until it hit the second prime, submitted it, and within a few minutes the solution was hacked again. So what the hacker did was they actually ran the same code on the machine because the person didn't initialize random seed, so he just typed for the default one. And even if you do initialize the random seed in the standard textbook way, so srand time will, so you take the current timestamp as the way to initialize your solution, it's still not really foolproof. It's already harder to hack because you have to guess which of the few possible timestamps will be in the server. But it is reasonably possible, and problems like this have been the source of a downfall of several internet casinos. So there has been an internet casino that has published their shuffling algorithm to make sure that the people trust them more. Do you are shuffling guests correctly, using this algorithm, and you are using the current time to initialize a random seed. And then if you sit down at for example, a poker table at the virtual casino, then you could just run through the several possible random seeds that are corresponding to the current timestamps and find which one of them matches the 2 cards in your hand. And then you know the other cards are on the table. Suddenly, the game of poker starts being much, much easier. There have also been cases when casinos published incorrect shuffling algorithms in order to make sure that people trust them. This is the shuffling algorithm we are using, and then somebody realized that the shuffling algorithm is completely broken. It doesn't leave any some cards in their places here, so it is guaranteed that the card that started on place N will not end on place N and something like this. And this skewed the probabilities enough again that people were able to misuse it somehow. So when using randomness in contests or in real life, be careful about it. It's not a magic wand that will not solve all your problems completely. But if you know what you are doing, you can often use it to your benefit. And in particular, in competitive programming, randomized algorithms, if you are encountering a problem where they can be used, can be really easy to implement. So again, similarly as you can do with the greedy problems I mentioned yesterday, the advantage of randomized algorithms is the simplicity. The amount of code is short, the code is reasonably simple, you just need to be able to tweak the constants so that they work with high probability. Alright, that's enough for today. Now it's lunchtime.
Yes.
Hein? Vamos começar. Que isso, cara?
Ah, eu falei isso na live stream. Desculpa.